we've been used to taking derivatives of things like, say, this, y equals square root of 16 minus x squared, right? We know how to take the derivative of that. But what about functions that are actually implicitly defined? In fact, they may be curves that on the whole aren't even functions. For example, if I take x squared plus y squared equals 16, okay, you guys are going to say, well, these are pretty much the same thing. Well, almost, right? Because this is the whole circle of radius 4, and this one is just the top half of that circle. So this is defined explicitly, y is a function of x. Here, this is not a function at all, as we know. This fails the vertical line test. In order to make this a function, and solve for y, I need to make sure that I'm only using 1/2 of the circle, right? So it's not a function until I'm able to solve for y. Now, I can solve for y, take plus or minus the square root. I happen to take plus square root here, and then take the derivative. What if I can't solve for y? What if I have something that's a little bit uglier than just this nice little circle here? Like here's a, no, I think I had x. X to the 4th, y cubed equals 12xy plus 3x squared, okay? What about that? I don't even know what that looks like. And I certainly don't know how to solve for y in terms of x. This would be really difficult. A lot of algebra, not worth the trouble, not worth the time. But look, if I look at that, in fact, it's kind of nice. You can make Desmos graph it. You just put it in, just put the equation in, right? So just put this equation in the way I wrote it, 3x squared, sure. And it looks like this. Okay, it's some kind of funky graph. It's not a function, but just like the circle, you can imagine that if I specified different x and y's, let's say I'll take this branch over here, or maybe I'll take this branch up there, or I'll take that branch, no, not like that. I'd have to go like this, and then I'd have to go like this, and I have to go like, so I could break it up into pieces where it was a function. On each of those pieces, if I could solve for y as a function of x, I could use my chain rule, but that's a lot of work and I would have to solve for y. So what we really need is a way of using a equation like this and figuring out what the derivative is without having to solve explicitly for y. So there is a way to do that, and it's called implicit differentiation. So implicit differentiation rather than having what we have here, which is y written as a function of x, we're going to have some messed up thing maybe where all the x's and y's are together. And so it might be like this, or you could write it as, we'll call it big F of xy equals 0, right? So I can put all that over. Right? So, but what you can do by implicitly, well, when I say implicit differentiation, what I mean is I've got something like this. I'm going to consider y as the dependent variable and x as an independent variable. So I'm going to consider y as a function of x. I'm just not going to be able to write it that way explicitly in a formula, but I'm going to be able to consider it that way. And then in order to take the derivative, I'm going to take the derivative with respect to x. So I'm going to take d dx of the equation. Okay? In a situation like this, I just take d dx of both. Well, you're going to take d dx of both sides of the equation, but if it's 0, it's 0, right? So here I'm going to take the derivative with respect to x of both sides. The trick or the thing that you have to remember is that y is a function of x. So when I take the derivative with respect to y, I have to use the chain rule. Okay, when I take the derivative with respect to x, I'm just taking the ordinary derivative with respect to x. Maybe I have to use the chain rule if it's a complicated function, right? But when you take derivative of a, of an expression with y, need the chain rule. And so what I'm going to be able to do in the end is actually solve for what dy dx is. So let's do that with this one. You know what I'm going to do? I'm going to erase this. I'm going to start at the top because there's some work here that needs to be done. So what I'm going to do is I'm going to take the derivative of this. I'm going to take the derivative of both sides with respect to x. So the derivative with respect to x of x to the 4 plus y cubed equals the derivative with respect to x of 12xy plus 3x squared. So there's some little subtleties that you might need to pay attention to in this. Okay? Remember, I'm solving for dy dx. I'm going to have a dy dx throughout my equation here. But I'm just going to go ahead and say, so the derivative of x to the 4, okay, it's 4x cubed. I'm taking the derivative with respect to x. Now I've got the derivative of y cubed, but I'm taking the derivative with respect to x. So it's just, again, I'm just using the chain rule as if it were a u. I will take the derivative with respect to y, and then I multiply by dy dx, right? So it would be 3y squared dy dx, because I want to be thinking of y as an expression, a function. I don't know what y is, but I do know that it's depending on x. So since I'm taking the derivative with respect to x, I have to get a dy dx whenever I'm doing that. Okay, now on the left hand side. Now I've got something a little more complicated here because I've got x times y. So y is a function and x is a variable. They're multiplying by each other, so I need to do the product rule because I'm thinking of these as two separate things. It's not that they're two separate variables. It's one is my variable, which is x, and the other is my function, which is y is dependent on x. So when I see them multiplied by each other, I have to think about it as two things multiplying by each other, like if it was x squared sine x, right? If I had x squared sine x, I want to take the derivative. I've got two things multiplying by each other. I have to use the product rule. So it's the same thing here. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. And I'm just going to put in the 12 with the x, but it doesn't really matter where it goes because it's just multiplying by 12. And then my last one is easy. I'm just taking the derivative of this. This guy's just going to be 6x, right? Okay. So let me clean that up a little bit. There's actually nothing to clean on the left-hand side here. This is just fine the way it is. 4x cubed plus 3y squared dy dx. And then this is 12x. The derivative with respect to y is just going to be my dy dx. And then here the derivative with respect to 12x is going to be 12. So I have 12y plus 6x. Now what I want to do here is solve for the dy dx, okay? Because that's my goal, is to find the derivative of y. Even though I don't know what y is explicitly, I can find out what the derivative is. So I'm going to put everything with the dy dx on one side, everything else on the other side. So I have 3y squared dy dx minus 12x dy dx equals minus 4x cubed plus 12y plus 6x. Okay, I can pull the dy dx out here. I'm going to have 3y squared minus 12x, and then I'm just going to divide it out. 3y squared minus 12x. Okay, so this is the derivative of that function. You'll see, again, I started with something that was implicitly defined. It was mixed up. And here I've still got my x's and y's. They're still mixed up. It's not the derivative written as a function of x. It's got x's and y's, but that's what I would expect, and that's perfectly normal. Now, let me just, I'll do a couple more, maybe in a second video, but let me just graph some. You know what? Let me just start another video and graph them as well there and take a look at maybe solving some other questions.